Okay, so our next speaker is Sriranga Kashyap. He will focus on open source methods for MR image segmentation and registration. Sriranga is an interdisciplinary scientist at the Kremlin Brain Institute in Toronto, Canada, and he specializes on advanced neuroimaging at 3 and 7 Tesla. His research focuses on developing innovative acquisition and analysis methods for high-resolution MRI, with applications in clinical and cognitive neuroscience. He also enjoys imaging challenging brain areas, integrating multiple data modalities like genetics and histology with MRI to study the human brain. So whenever you're ready, Sriranga, please take the floor.
Okay, I'm unmuted, I think. Going to share my screen. Thank you for the kind introduction. And just starting my timer. Hi, everyone. Thank you for attending this brief tutorial on open source methods for image segmentation and registration. My name is Sriranga Kashyap. You can call me Sri. And before I get started, I just want to make sure that everybody realizes that the work that I'll present is built on efforts of many developers, researchers, hobbyists, and they share their code openly without any hesitation so that it helps one another. And one of the things that you can do to give back is to cite their work quite generously. And by this, I mean their individual papers, the algorithms they worked on, in addition to the toolboxes. And more importantly, share positive feedback when things are working. All GitHub issues are always, this is not working. It's quite negative. But also say, hey guys, thanks. That was awesome. It worked for me. And thanks to everyone who contributes to open science. So this is an overview of my talk. It's not very long. It's quite brief with some examples. The first one is to check in on some of our community standard tools that we are very familiar with. Again, this is not an exhaustive list. I don't want to annoy anybody whose tool is not mentioned in the slide. They're all awesome. Everybody's doing amazing contributions. The second chapter would be on MR image segmentation. Again, these will be some examples from my own data. I'll cover the ones where it doesn't work and some of the tips and tricks you can use to fix it, and the same for registration. So I think this is one of the oldest, most famous ones, SPM. Everybody's familiar with it. It's available in Neurodesk as well. The important thing is that it has multiple plugins developed over decades and many derivative toolboxes. But the biggest downside often complained about is that it needs MATLAB, and MATLAB needs money, and not everybody has this. But over the past few years, I mean, you don't see this directly on the documentation page, but if you go to the GitHub page, you'll see that this is not the case anymore. A lot of people have been working on making SPM into a container. And this container, you can even use the SPM GUI if you're very familiar with it and you want to continue using the GUI. There are also ongoing efforts to port it to Julia and Python. So you can have a look at that. And of course, everybody's favorite, it works with NePipe and integrating it with the rest of your imaging pipeline. FSL, again, another famous tool. Tui just gave an example of BET, which is widely used. It consists of compiled binaries. So you just download it and you're off to the races. It works very well. The code is available on GitHub as well. So if you want to go look into it, see what it does, it's documented. It's a workhorse that is the basis for many useful pipelines like fMRI prep and HCP. Again, available as a part of NePipe that you can use to combine with maybe some parts of SPM. And one of the reasons why I use it a lot is because it comes built in with tools for perfusion imaging analysis like ASL, and it has this Python interface. And a special shout out to Tom Kirk, who's developed this nifty little toolbox called Regstrix. It's a Python wrapper that really helps you with FSL registrations, combining linear and nonlinear warps, chaining together multiple registrations without having to worry about, am I doing it right? Is it the right convention? It comes in clutch if you use FSL regularly. So please have a look. Um, And then there's AFNI, obviously, again, compiled set of binaries, easy to install, mostly easy to install, has a lot of dependencies, but once you have it sorted, it works really well. And I would argue that it's one of the best documented set of MRI tools, also most comprehensive. So if you just want to learn um, cost functions, how to use, what choices to make, some of the things that are described in the notes are always helpful. Um, Another reason why it might be very appealing to some people is that it has expert developed Python and shell script that can help you build pipelines. And you can perform tasks that often require multiple commands and exact knowledge of what needs to be input, what needs to be output. Am I giving it the right file? With these Python wrappers, all these things are made easy for you. Um, One of the reasons, again, that I use it a lot is because it has some recent developments that enable laminar fMRI analysis, which is looking at fMRI of cortical layers, typically 7 Tesla submillimeter resolution fMRI data. And again, works with NePipe as the rest of the tools. And quite quickly, a few honorable mentions. FreeSurfer, everybody's favorite T1 segmentation surface tool. Ants, so Ants X, because it's the ecosystem, they have a Python interface, R interface. There are some neural net based tools now as well. And a set of tools by the developers of ITK Snap, which include C3D and Greedy. And of course, like I said, there are many more. There are many openly available tutorials to look at each of these different tools, how each of them approach the registration problem or segmentation problem, what tools they have. So please have a look at them. If you are new to the MRI community, then you will soon realize that each of these toolboxes locks you into an ecosystem. It's like you're an Apple user, everything works with Mac, iOS, iPhone. And what I mean is, if you're trying to combine SPM, AFNI, and FSL transformations, it is nigh impossible. It's quite early in the morning, so forgive me for that. But almost impossible, because again, our friends in the community are developing tools like knee transforms, which is a part of the NIBabel, NIPy community for this specific purpose. There are other tools like C3D, C3D Affine tool, FreeSurfer's LTA convert and warp convert, which would allow you to change conventions, go from FSL to ANTs, back and forth. And this is why it's important to always check conventions. What are you using? What did you use in the previous step? And using the right fixed and moving images. So given that brief overview of all that exists, I mean, there are a lot of links that will be put in the description. You can have a look at them at your leisure. I'll move on to chapter 2, which is MR image segmentation. As you might have heard before, typically involves brain masking, skull stripping, and tissue segmentation, where you want gray matter, white matter, CSF, and parcellations and so forth. So I'm going to try to see if I can get a pointer. Yeah, I think you can see the pointer. So this is a first use case, just to demonstrate, where I have a 7T whole brain anatomical image. As I mentioned earlier in my talk, I'll show you examples of things where it doesn't go well. If you're using 3T standard 1 millimeter T1s, almost every tool that you use will work more or less out of the box. These are for problematic use cases, information that you might not find in the YouTube tutorials. So it's important to note that these defaults for these kind of data sets may actually be suboptimal. So you would need to tweak it a lot. For instance, with FSL bed, if I just do the input output, not change any of the additional parameters, I end up getting this chopped up, half-eaten brain. 3D skull strip works slightly better because it has some intensity and homogeneity correction steps, but it still eats up a lot of the edge of the brain. One of the tools that I really do like is recently, it's a deep learning tool in FreeSurfer called SynStrip. As you can see, it really doesn't care that there are these intensity inhomogeneity gradients. It just gives you a nice brain mask that has everything. There is a bit of non-brain there, but it's good for a start. Even if you correct the intensity and homogeneity with your favorite bias correction tool, N4, SPM, what have you, you'll still end up with problems with these data sets. So these days, with these kind of challenging data sets, have a look at SynStrip. It might help you a lot. There is another special use case for people who do 7T MRI, and that is when you use dielectric pads. These are special pads that help you get a bit more signal if you're imaging the hippocampus, let's say. And with these dielectric pads, this is how they look like in a T1 image, this little uh, almost the same grayscale intensity as some of the tissue. And this really throws a wrench in most of these tools. So after fighting quite a bit, I have this little shameless plugin of my script, which will just create a mask around it and clean it up and still retain the skull. So you can depad the data and then continue using your other favorite tools. This is the second use case. In this case, I'm looking at fMRI data. So the previous data set, as you saw, was a T1, which is your structural scan. This is fMRI. And here you can see that this is the original data. You use SynStrip, and then you get this beautiful brain mask. Alternatively, if you have some challenging data sets, you have thresholding methods that you can consider using. It's a bit of a learning curve, but most of these tools have these morphological operations built in that you can do. So you can do kind of an intensity threshold to separate this bright signal from the dark signal of the background. You can erode the mask, kind of eat up the edge voxels and kind of clean up the skull. And then you can clusterize it and get like the largest cluster that's there. And now you see that it has like a brain-like shape and it's in the middle. So you can inflate it again using dilation. And now you have a brain mask that is very similar to SynStrip. But again, bit of a hassle. If you can take the functional route, why not? And here I have a little video. Let's see if it plays. So this is just using ITK Snap, which is a GUI which can do a lot of different things to create a brain mask for a partial brain image of an fMRI dataset. So this is like a 0.7 millimeter image that you typically acquire in 7T laminar studies. And brain masking this with even SynStrip or standard tools is always difficult. So what you would do is you would go to this little snake tool that's in your ITK Snap toolbox, and then you would use these red dotted lines to kind of shrink the image, make it smaller to fit as close to the brain area that you want to mask. And once you have this, you can click on the segment button and it gives you this little window. And in this little window, you have many segmentation modes that you can choose. In this case, I do something quite simple because it's an fMRI image. I go to clustering, and in the clustering, I say I need two clusters. I just want the brain, not the background. And then there's this little recycle symbol, which means reinitialize these clusters. So just press on it a few times until you get an image like this. And once you get an image, drop a couple of bubbles. and think of it as a way that it kind of fills into this mask that you created. And then if you let it, flow, so to speak, um, then you end up with this nice little brain mask that you can use for the rest of your analyses. It's quite fast. Like once you get used to it, it takes about 30 seconds for the data set. Moving on quickly. Yeah, for whole brain use cases, I don't have to mention you have FreeSurfer, you have Cat12. There's also this little extra thing, again, another shameless plug, which can help you fix MP2 range data sets. Have a look. So if you have MP2 range, you need a bit of extra processing to prevent FreeSurfer from doing funny things like putting a gray matter surface on the sagittal sinus. So it helps you clean things up quickly. Tissue segmentation. Um, this again in ITK Snap. You can see I'm using the same snake operator in the top there. I'm using this red box to crop it into one small brain area that I'm interested in. Again, this can vary based on your requirement. Not sure how visible it is, but this little box over here is what I'm looking at. And now what you can do is again click on this the special flag here called resample ROI. What this allows you to do is, for the sake of segmentation, really upsample your data set in the GUI itself. So you can say I want a 2x upsampling. So if you have a 1 millimeter data set, you say I will segment this at 0.5. And in this case, it's 0.7. So I say I super sample by 2 times. And now the data set is 0.35 millimeters isotropic. And it neatly takes you to only the cropped region that you want. And you can already see with the clustering approach, there are like segmentations there. But even if you do thresholding, because it's a T1, you can get a very good gray matter mask already. And you can play with this threshold. And again, the same as before, you drop a couple of bubbles in red. This time I'm making the bubble smaller because it's a very thin strip that I want. And you let it flow. And once it flows through, now you have your gray matter beautifully, more or less segmented. If you're doing laminar fMRI, you would again pay more close attention, clean this up, tweak things manually, but it's a great starting point, which is automated. You can also do some things like make a mask. Say I just want that region, I want something quick and dirty. Make a mask for the region that you want in ITK Snap. This you can do with the brush tool. You can select the shape of your brush, make it 3D isotropic so you get like a box. Save this, and then you can use your favorite tool to do like k-means clustering or any kind of clustering that you want. And here you go, like in less than 30 seconds to a minute, you have segmentations, which look quite good as a starting point in a small region. Now, MR image registration. I think I am okay for time, but I'll try to be a bit quick, but you can slow me down in the recording later. So I'll only talk about 2 applications, fMRI to anatomy and partial to whole brain. Again, problems that you might not see in YouTube tutorials. Important tips: proper initialization of your registration, super important. If you're expecting the algorithm to somehow understand what you want, will not work. So help it along. The algorithm is dumb. How do you do this? Give it a good starting point. If you ask it to figure out the starting point, it'll get stuck in local minima. It won't converge, or even if it does, it's a bad result. And again, you end up repeating it, changing cost functions, changing parameters, ranges, rotations. You waste a lot of time, not necessary. You can always initialize, and I'll show you how to do it. So depending on the tool, in this case, ITK Snap and using it with ants because they work together really well. Here is an example. Again, this is ITK Snap. What I've done is I have the T1 as underlay, and I have my fMRI images overlay in color. And you can see that the fMRI image is kind of wonky. It's not facing the right way. So if I would just want to register this, it may not really work. So what I would do is I would go to Tools, Registration, and then it gives me this little registration window. And there you have the interactive tool in the manual section. And with the interactive tool, what you can do is you can visually rotate it, shift it around, move things along. And once you have it approximately aligned, you can go to the automatic part and now ask the algorithm to, okay, give me a good starting point using your underlying registration algorithm, and hit run with the coarsest and the finest levels being 1. And now you have an excellent initial registration. And now you save it into a transform file, and you can use it for all registrations that you want to use later on. Ooh, next slide. There we go. This is another quick example in a case where you have multi-session data. So you've acquired on day 1 the T1, but then you only acquired fMRI because you're trying to maximize your SNR for your statistics. So on day 10, you have no T1. And if you look at the images, this is how they might look. They're in 2 different places. Again, here, you can make your life easier by going to the visual manual tool, but this time there's a match by button at the bottom. And here you can say, hey, match it by the centers of the image, or match it by the centers of mass. And these things will help you do this large move fairly quickly so that the 2 images are somewhat in the same place. And then you can nudge them along and kind of make it fit on top of one another. And then the steps are the same as the previous one. And now you have something that mostly overlaps. But again, this is not really an ITK Snap thing. You have this working with FSL as well. It's called the nudge tool. It's available in Fossilize. If you go to tool and you select nudge, you can now move the brain images along. I'll just let the video play while I speak. It gives you this little window, and you can manually move things around. You can save this and use it with Flirt's init flag. Init is for initializing your transform. This time you have a custom one. You could also do something like obtaining an initial matrix with cost normalized mutual information, and then use that to initialize a BBR transform. Often helps you save a lot of time in having these algorithms figure it out. It's also available in AFNI. So if you go to define data mode and plugins, you'll be able to select the nudge plugin, which is seen here at the bottom. And it's not a video, just a screenshot. Just some careful visual nudging that you can do in AFNI as well. If you're just playing around, make sure you hit clear, or else you'll be applying like multiple transformations and you're wondering, oh, I changed it by 0.1. Why is the whole brain rotating? So be careful when you use it. It'll output the 3D rotate command to the terminal, which you can copy and use. Again, in this window, click on the help part. It's a gold mine. It'll explain everything. Some tips for registering. I'm almost done. I have a couple of slides. fMRI to anatomy. So this is your EPI to T1. Use the visually guided initialization strategies that I've shown, or try to use some command line initialization. Always keep in mind that it's fine to register in multiple iterations, as long as you can combine them into one transform and apply it later in a single step. You can use many tools for this: Convert XFM, AFNI's tools, and the Python libraries that I showed earlier. Another thing that might help with some data sets is if you're working with fMRI data, try to fix the spatial distortions first, then they align with the anatomy better, and you might get a better registration out of it. Again, for most whole brain applications, every tool that you have works nearly out of the box. Partial brain to whole brain, not so much. Again, some tips. You can try to move the larger volume to the smaller volume. So instead of always aligning EPI to anatomy, consider aligning the anatomy to EPI. You could also do something where you can crop the anatomy. So if you're only looking at the visual cortex, try to crop the T1 to only have the visual cortex and then try to register with your EPI. Again, you can use the visually guided initialization strategies. Yeah, you could also speed this up with command line things. For instance, AFNI has this at align centers. You could do this with ANT's registration as well to use geometric centers. Again, register in multiple iterations, combine them into a single transform. It's completely fine. Another tool tip that really works is using fixed and moving image masks. Many tools support this. If you're uncomfortable or you don't know which ones to use, just mask the regions out, keep it in the same space, and then compute your registrations. Then you know that the algorithm did the best job for that region that you want. Again, with fMRI, maybe fixing spatial distortions first really does help. Okay, to summarize, all tools have their strengths and limitations. It's okay to mix and match them, but very carefully. Visually guide segmentations and registrations when needed, nudge the algorithms along, know which tools work together. ITK Snap and ANTs, FSL Free Surfer, I don't know. See if they can use each other's transformations. Never use a drill for a hammer's job. Use the right tool for the task. If something is not working, maybe it's the tool. Switch, see if another tool can do the job better. Again, I do not recommend one way over the other. The best method is the one that works for your data. If you're feeling adventurous, I would strongly suggest to look at these examples in the scikit image and the registration pages of Simple ITK. And that was really all from me. Thank you for your attention.